to start, well first, homework for Tuesday, pick any 10 problems from chapter 6. If you want to do the first 10, fine. Pick any 10 you want. In chapter 6, the later problems are not necessarily longer or harder. They problems just go in a certain sequence. They involve capacitors and inductors. The earlier problems involve more graphs. The later problems, some of them are questions like combine these capacitors in series, combine these capacitors in parallel, see what you get. They're not necessarily easier or harder. So pick any 10 you want. I wanted to start by just talking really briefly about lightning. That's kind of an everyday application of circuits. And it's also going to connect a little bit later on into our discussion of practical capacitors. So first let me ask you, what do you know so far about lightning already? What is a lightning bolt? Spark. A spark. And what's a spark?
Charge.
Okay, I won't ask you what's charge, because I don't have a great answer for that either, right? It's just charge, motionless charge.
There's like a charge built up on one side, and then for some reason it arcs across to like a negative red.
It rips green.
It rips electrons off of
Yeah,
the air.
ripping is the word you're looking for.
What rips the electrons off the air ball?
Electric field.
Okay, you're saying all the right stuff. You're close, but just saying the electric field rips it off. A strong enough electric field eventually would rip it off. That's not usually what causes a lightning bolt. All the time in the air, there are atoms, and those atoms are constantly crashing into each other. Agreed? And so all the time, once in a while, an electron gets knocked off an atom, then maybe goes back and recombines with another atom later on. So there's always in the air, at all times, a couple stray electrons moving around. There, okay. Now, if you apply a large enough electric field, what is an electric field? Let me pose that question to you. Suppose I say I have an electric field of 10. First, what units should I give for that electric field?
Newtons per coulomb? Yeah.
Okay, newtons per coulomb, correct. It's force per charge. Because electric field is a measurement of how much force you'd have on a charge if it were there. You can have an electric field even if you have no charge. It's a hypothetical, sort of. It says, how much force would I have if I put a charge there? So it's force per charge. So if I had a charge, there'd be a force on it. So if I have an electric field, if I then have a stray electron, which I do in this air, I have some stray electrons, there'll be a force on it. If there's a force on a stray electron, what's the electron going to do? It's going to, well, I know what you mean, Roger.
Yeah.
The force will cause it to accelerate. It won't go towards the force. I know what you meant. A force isn't a thing, it's an interaction. So it's going to cause the electron to accelerate. That electron will accelerate until it crashes into another atom or some other molecule, which normally doesn't take that long. The air is full of molecules. The electron will accelerate a little bit, and it will kind of bump kind of gently, or it won't necessarily cause catastrophic damage because it hasn't gotten going that fast. But if the electric field is strong enough, the electron will accelerate fast enough before it crashes into the next atom that it gains enough speed, and when it does crash into another atom, it crashes with enough energy that it can knock off one of that atom's electrons. So suppose I have an electron. Suppose the electric field has just exceeded some critical point where the electron now can get going fast enough before it hits another electron, before it hits another atom. That when it hits the other atom, it knocks off 2 electrons on average. As soon as it knocks off those 2 electrons get moving, get accelerating because of the same electric field. They now get going fast enough that they hit more atoms, and when they hit those atoms, on average, they knock off 2 more electrons each. So if I have 1 electron in the air, that electron causes it to crash, or that electron will speed up, crash, cause more electrons, those electrons cause more electrons, and before you know it, there's gazillions of these electrons which then make the air act like a conductor. And then, so if you have a strong enough electric field between, say, in the air, between the Earth and the clouds, then if you had any stray electrons, which we always do, those electrons will get going and cause there to be potentially a corridor where you have a very conductive area, and then whoosh, all the charges can, since now it's conductive, all the charges can flow through it, and you get that flow of charges would be the lightning bolt. Why do you hear a lightning bolt? Thunder, the lightning bolt. Why do you hear it? Why can you hear a lightning bolt?
The electrons crashing into each other?
No, good thought though.
It's actually the air crashing back into itself.
Okay, so as all this charge is flowing through the air, you think the air gets hot or not?
Yeah, really hot.
Yeah, really hot, and so it might expand very rapidly. Hot
It's
air
like a vacuum.
will expand. Well, it's not a vacuum, it's just air.
Well,
And will cause those air molecules will then crash into the air molecules around them, which crash into the air molecules next to them, which crash into the air molecules next to them, and that's precisely what sound is. So what a speaker does is it just moves the air back and forth. So a lightning bolt is a very sudden poof, where that air gets all pushed out from that spot, and then you can hear it later on. Why do you see a lightning bolt? Well, the light, it can be produced by electrons. Are all getting excited in different energy levels, and when an electron changes energy levels, it could release that energy in the form of light. And some of that light you can see, so you can see a lightning bolt. If the electric field isn't big enough, then what will happen if I did get an extra electron, which I do, I always have extra electrons in the air, that electron will accelerate due to that electric field, but it won't accelerate enough before it crashes into another atom to get enough energy to knock other electrons off. So as long as the electric field is small enough, these extra electrons will accelerate. They will just kind of move. Oh, if you've seen like some of those things where you have like pegs, you put like a little disc and it kind of flicks through those pegs. It'll just be kind of like that. It won't get enough energy to break the pegs. It'll just kind of click its way through. Each time accelerating a little bit, crashing into another atom, accelerate a little bit, crash into another atom, but it won't get going fast enough before it crashes into another atom to knock more electrons off. So if the electric field is small enough, no sudden change in the air is going to happen. If the electric field gets just barely big enough, just bigger than some critical amount, then those electrons, as they crash into other atoms, will make more electrons, and it will be a chain reaction that will suddenly cause that lightning bolt or spark, as